Welcome to this online training about standard interfaces used in Platform Designer. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the email address provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. As noted when you registered, this training is a required prerequisite for our Introduction to Platform Designer instructor-led training. If you have any questions about this training, please feel free to keep track of them and ask the instructor when you attend the live class. If you're interested in this full-day class about the Platform Designer System Integration Tool and not already registered, click the link to register for an upcoming session. Even if you are not planning on attending the instructor-led training, this online training will help you get familiar with the most common standard interfaces used by off-the-shelf IP and that you can integrate into your own custom components in Platform Designer and elsewhere in the Intel Quartus Prime software. You'll learn about the signal roles that make up the standard interfaces, which will help when you are mapping the top-level signals for your own designs to those roles when building custom components. Finally, you'll know where to go for more information about the supported standard interfaces, including documentation and further training. Before we begin, we wanted to highlight some changes in common terminology we'll be using, especially when describing system interfaces. There are a number of instances of non-inclusive terminology in technology. As part of Intel's commitment to inclusion, a number of common terms are being phased out in our software and documentation in 2021. We're in a transition phase, so you may still see some of the old terminology, but for this training, the terms master and slave have been replaced with host and agent, the terms that will be used in the Intel Quartus Prime software going forward. Note that other vendors may use different names as shown. Listed here are the main types of standard interfaces supported by Platform Designer for the design and integration of system components that will be discussed. Every component makes use of one or more of these standard interface types. This is not a completely comprehensive list. There are some additional standard interfaces and variants of these standard interfaces also supported by the tool. See the documentation and other resources linked to at the end of this training for complete details. As the supported standard interfaces are discussed, remember that while we focus on their use when connecting components together within a system design, any interface can be exported out of a system for use elsewhere in a project, or to be connected to I/O pins. Let's start with clocks. Clock interfaces generate or receive clocks to synchronize communication between Platform Designer components. Clock signals are used by other component interface types and can be used by the internal logic of components themselves. Clock input or sync interfaces provide an input clock to a component. The clock is used to synchronize transfers on other component interfaces and can also be used by a component's logic. Clock output or source interfaces are used by components that can generate and send a clock out for use by other components. The best example of a component with both clock input and output interfaces is a PLL. PLLs in Platform Designer have a reference clock input interface that is used as the PLL's source clock. PLLs may also have an Avalon memory mapped interface, discussed later, to control PLL settings. This memory mapped agent interface is synchronized to the clock input interface. PLLs are configured to have one or more clock output interfaces to send generated clocks out for use by other system components, or to be exported out of the system. Every component must have at least one clock interface. A clock interface can be either an input to or an output from a component and consists of the single clock signal. For every standard interface discussed in this training, all the required and optional signals that make up the interface will be listed in tables like the ones shown here. The named signal roles in the tables are the names used by the component editor in Platform Designer. The listed signal role names should be used for the correct mapping of signals in your own custom designs to the appropriate signal role in each supported interface type. You'll learn more about the component editor in the Introduction to Platform Designer class, as well as in other trainings linked to at the end of this training. The next interface type is the reset interface. Like clock interfaces, reset interfaces provide basic logic functionality, in this case, allowing a component to receive and generate reset signals. A reset input or sync interface connects a reset signal to a component. The reset can come from inside or outside the system. The component can use this reset to return its other interfaces and internal logic to a known state. A component can also generate a reset and send it out to the rest of the system with a reset output or source interface. Both reset input and output interfaces must be associated or synchronized with a clock interface. This association is shown in the clock column of the System Contents or System View tab in Platform Designer. In the example shown here of a custom button debounce component, the reset input interface is highlighted, and the clock column for this interface indicates that it is synchronized to the interface in the component named clock. Notice that other interfaces in the component are synchronized to the clock interface as well. While not required, it is recommended that every component have at least one reset interface. Platform Designer will generate warnings for a custom component that does not include a reset input interface. The reset signal can either be active high or active low. Optionally, a reset request signal can be used to prepare a component for reset, especially when asynchronous resets are used. If the reset request signal is missing on one side of a reset interface connection or the other, or there is a mismatch between an active high and an active low reset, logic will be added to the Platform Designer interconnect to accommodate the differences. We'll now look at the Avalon interface standards, starting with Avalon Streaming. The Avalon Streaming standard is used for high-speed, unidirectional, point-to-point data transfers. Like all standard interfaces, Avalon Streaming is fully synchronous and is flexible enough to support both simple and more complex transfer requirements. Perhaps the biggest benefit of an Avalon Streaming interface is the ability to support high bandwidth data transfers with minimal latency. Avalon Streaming can be used anywhere you want to move data from one location to another quickly, but typical uses include multiplex data streams of broadcast applications, packetized data from networking applications, and DSP data from video applications. There are two variants of the Avalon Streaming interface, standard and credit-based. Here are some basic concepts about Avalon Streaming that are important to understand before examining the standard itself. Avalon Streaming consists of two interfaces, the Avalon Streaming Source and the Avalon Streaming Sink. A source interface launches data on rising clock edges, while a sink interface latches data on rising clock edges. By default, both interfaces must be ready to send or accept data every clock cycle unless additional interface signals are implemented to stall data transfers and implement flow control. Back pressure is the term used for this flow control mechanism. Both the source and the sink can stall a transfer using the appropriate signals. Avalon Streaming supports multiple channels of data. These can either be physical channels made up of multiple data paths or logical channels that are multiplexed through a single physical link. A symbol represents the smallest unit of data that can be transferred through a channel. This is typically 1 byte. A beat is the single cycle transfer of one or more symbols. When creating your own interfaces, you can specify how many symbols are transferred per beat. One of the flexible aspects of the standard is that the formatting of the data is completely application or component specific. The standard does not define the data format. The interfaces are only responsible for sending and receiving data. It is the logic controlling the interfaces that is responsible for formatting or manipulation of the data. As mentioned, there are 2 variants of the Avalon Streaming standard. Let's start with the original standard. Avalon Streaming interfaces are made up of the signals listed here. The ready and valid signals are used for data qualification and handshaking between the source and the sink. The ready signal is for true back pressure from the sink. A source cannot send data to a sink until the ready signal is active. The valid signal validates the data from the source, so the sink will not accept data until valid is active. The remainder of the fundamental signals can be customized for the application. As mentioned, the data transferred on the data signal can be formatted as desired. The channel signal can be used to identify different logical channels of data being transferred across the interface. The error signal can be used to mask off errors in the data. Both the source and sink would need to be designed to generate and interpret the error signal appropriately for the application. Avalon Streaming also includes dedicated signals for packetized data transfer. The start of packet and end of packet signals are self-explanatory. The empty signal can be used along with end of packet to indicate at the end of a packet transfer that a certain number of data symbols in the packet are empty. For example, with a 32-bit data signal and a symbol size of 8 bits, on the final data transfer, when end of packet is asserted, if empty is set to 3, then the 3 least significant bytes of the 4 bytes transferred are empty. See the Avalon specification, linked at the end of this training, for a timing waveform example that illustrates the use of the packet transfer signals. Note that when creating custom components with Avalon Streaming interfaces, you don't have to use all the signals listed. Only use the signals that are needed to implement the desired functionality. Here are 2 simple examples of Avalon Streaming interfaces. In the first example, the Avalon Streaming source produces the valid and data signals. The data signal presents the information, and the valid signal serves as an enable to the sink to indicate that the values on the data signal should be accepted. If the source has no data to send, it deasserts the valid signal. In this case, the sink has no way to stall the transfer, so it must always be able to accept data when the valid signal is asserted. In the second example, the source and sink interfaces also include the ready signal. The ready signal allows a sink interface to stall or apply back pressure to the transfer. A source with a ready input must not send data when the ready signal is deasserted. This example shows a more complicated interface, again showing the flexibility of the Avalon Streaming standard. In addition to the ready, valid, and data signals, these interfaces include the channel signal and the packet transfer signals. Again, if either side is missing any of these signals, logic is added automatically to the Platform Designer interconnect to appropriately control the missing signals on the other side of the interface. Most of the standard interfaces supported by Platform Designer include interface properties that can be adjusted to customize how the interface will be implemented and function in a system. These properties are usually specified during the creation of a component, but some of them may be exposed as component parameters. Listed here are some of the parameters available for an Avalon Streaming interface. The data bits per symbol property indicates how the data being transferred is organized. By indicating the number of bits per symbol, the number of symbols per transfer is defined. For example, with a 64-bit data bus, if the bits per symbol is set to 16, then each transfer contains 4 symbols. This information is used to resolve connections to other interfaces with a differing number of symbols. The readyLatency property indicates how soon a source can send data and how soon a sink can receive data. For example, with a source, readyLatency indicates how many cycles occur between when the ready signal is asserted and valid data is actually available, or between when the ready signal is deasserted and valid data is no longer available. For a sink, readyLatency indicates how many cycles occur between when the ready signal is asserted and when the sink is actually ready to accept valid data, or when the ready signal is deasserted and the sink will no longer accept valid data. The readyAllowance property is often used along with readyLatency. It indicates how many additional transfers can happen from source to sink after ready is deasserted. This property must be greater than or equal to the value of readyLatency. We'll look at how these properties work in a moment. Finally, the max channel property indicates the maximum number of channels supported by the interface. This property must be set if the channel signal is used. There are many more properties available for an Avalon Streaming interface. See the Avalon specification for a complete list and details on each. Here's an example on the use of readyLatency and readyAllowance. By default, both are equal to 0, meaning that the sink is always ready to receive data the same cycle the ready signal is asserted. For this example, readyLatency on the sink is set to 1. readyAllowance is automatically set to 1 as well, since it must be equal to or greater than readyLatency. At clock cycle A, ready is asserted by the sink. However, because of the readyLatency of 1, the source must wait an additional clock cycle before valid data will be accepted by the sink, so it does not send out valid data until before cycle B. At cycle B, ready is still asserted and the sink accepts the data from the source. This cycle is referred to as a ready cycle because the sink is actually ready to receive data at this point. For cycle C, the sink has deasserted ready, but notice that valid data is still received by the sink. Even with ready deasserted, the ready from cycle B still applies to cycle C, making cycle C a second ready cycle. This also matches the readyAllowance property value of 1, meaning data is still accepted 1 cycle after ready is released. At cycle D, ready is asserted again, but like cycle A, cycle D is not a ready cycle, so no data transfer takes place. Note that if readyAllowance was set to 2, for example, cycle D would also be a ready cycle, allowing the sink to continue receiving valid data 2 cycles after the last ready assertion back at cycle B. Finally, cycle E is another ready cycle due to the ready assertion at cycle D. Since ready was held for only a single cycle, cycle E is the only ready cycle after cycle D. So as you can see, it's easy to adjust how the handshaking and back pressure work through interface properties. See the Avalon specification for more examples on the use of these properties. While Avalon streaming interfaces are very useful for high-speed data transfer, there are some issues to be aware of with their use. As you may have noticed, without added properties, any source or any logic adapter between a source and sink must respond immediately to halt data transfer when the ready signal is deasserted. extra logic is required to implement this feedback, as seen in the data path diagram here. This leads to extra levels of logic, which in turn could cause time enclosure issues due to the feedback loops themselves and the dependence on ready. Feedback loops are not hyperflex friendly, meaning that in hyperflex architecture devices, it is difficult, if not impossible, to optimize loop performance while maintaining the correct functionality of the loop. To achieve the best performance optimization in a hyperflex-based device, a design should look like the diagram shown here, a series of pipelined registers with only combinational logic between them. With a design like this, there are no dependencies between the previous and next states of the logic, and no backpressure controls that must immediately adjust the flow of data through the pipeline. This allows for optimal register retiming and optimization performed by the Intel Cortex Prime software when compiling a design for a hyperflex-based device. To create a more hyperflex-friendly interface, you can use an Avalon Streaming credit interface instead of the standard streaming interface. In a streaming credit interface, the sink provides a certain number of credits to the source to indicate it's ready to receive data, instead of using the ready control signal. The source can only send valid data out after it receives these credits and only as long as it has available credits. A credit is consumed for each data transfer, and the source needs to keep track of the credits it's been allocated. With this setup, the sink can provide credits at any time, and the source can use any credits it has to transfer valid data at any time. Using a streaming credit interface instead of a standard streaming interface creates simpler logic that can lead to a higher performance design, especially when used with retiming in a hyperflex-based device. However, the implementation does require more logic resources and will increase design latency due to the ability to more heavily pipeline the design. The higher achievable Fmax, though, does compensate for the increased latency. The flow for credit-based transfers looks like this. On the source side, the source must wait to receive one or more credits from the sink. When it does receive credits, it needs to keep track of the number of credits allocated. The sink is not involved with keeping track of the credits allocated to the source after the allocation. Every time the source transfers data, the credit count must be decremented by 1. The sink can provide additional credits at any time, even if the source still has credits available, but again, the source must keep track of this. The number of credits at the source can never be less than 0, and the maximum number of credits available is set with the max credit property. This can be set to a maximum of 256 credits. On the sink side, the sink can start sending credits to the source at any time after reset. It can send more credits at any time as well, even if a full data transfer has not yet completed. Here are the signal roles for a streaming credit interface. Most of the signals are the same as for a standard streaming interface. The new or different signals are update, credit, return credit, and the optional user sideband signals. The update signal is from the sink to the source and is asserted, along with the credit signal, to indicate to the source that it has additional credits available for use. The credit signal indicates how many credits can be added to the source's credit counter. The return credit signal is a mechanism for the source to return credits to the sink. For every cycle the source asserts return credit, it reduces its credit count by 1. The sink needs to keep track of these returned credits to know how many more credits it can give back to the source. The return credit signal can be asserted simultaneously with valid data. When this occurs, 2 credits are consumed in the same clock cycle, one for the data transfer and the other for the returned credit. Finally, optional sideband user signals are available for use with Avalon Streaming credit interfaces. The data transferred on these sidebands is completely user-defined, so care must be taken that both sides agree on the use of these signals. The packet user sideband can be any width needed and is asserted for the length of the transmission of a complete data packet. The symbol user sideband is asserted along with a particular symbol in the transmitted data. If multiple symbols are transmitted on the same clock cycle, symbol user must be wide enough to provide the sideband information for each symbol. For example, for a symbol size of 8 bits and a 32-bit wide data signal, 4 symbols are transferred each clock cycle. If 3 bits of sideband information are required for each symbol, symbol user must be 12 bits wide. See the Avalon specification for more details and to learn how missing signals on either side of the connection are handled by the Platform Designer interconnect. The implementation in hardware of a streaming credit interface connection looks like this. There are now essentially 2 paths, one going from source to sink for the data, and one going from sink to source for sending credits. With separate pipelines and knowledge through the credit system, there is no rush for providing data or credits, so it's easy to add additional pipeline stages to the data path. And, as mentioned, adding pipeline stages can greatly improve performance, especially in a hyperflex architecture. Here is a simple example of a streaming credit interface. At cycle A, the sink asserts the update signal and specifies a value of 4 to the source. The source would need to store this value to keep track of the number of credits it has available. Sometime later at cycles B and C, the source asserts valid and sends data to the sink, using 2 credits in the process. Again, after some time, at cycle D, the sink provides 1 more credit to the source, which is used for 1 more transfer at cycle E. The source finishes this example with 2 credits remaining. See the Avalon specification for additional examples and details on streaming credit interfaces, including an example of the return credit signal. Next, let's take a look at Avalon memory mapped interfaces. Memory mapped interfaces are used to connect one or more agent interfaces to a particular host interface. It is address-based, where the agent interfaces are mapped to address locations in a host's memory space, and the hosts initiate read and write transfers with those agents by issuing requests to those mapped addresses. A typical host uses a registered interface for this, issuing commands using control signals and sending and receiving data through separate data buses. Data transactions in the form of commands are initiated by hosts. Agents respond to these commands as transaction requests. Data can flow in both directions in the form of either reads or writes. In most cases, there is no direct connection between a host and an agent. A host initiates its read and write requests with the Platform Designer interconnect, not directly with an agent. An agent accepts commands from the interconnect and sends responses to the interconnect. There are some exceptions to this, most notably when using a tightly coupled memory that connects directly to a Neo soft processor without going through the interconnect. This enables the memory to essentially be used as a cache for the processor. But in most cases, the interconnect is added between host and agent. Memory-mapped interfaces are often used for accessing control and status registers. An agent interface will usually have a set of registers associated with it. In Platform Designer, a base address is assigned to the first register in the register file of the component, and subsequent registers are accessed at address locations offset from the base. The range of all addressable agents connected to a host is how the address map for each host is defined. It is also common for a component to have multiple memory-mapped interfaces. For example, a single component may have a host interface to initiate reads and writes to an agent, such as a memory, and an agent interface to allow another host, like a processor, to configure it. The interconnect handles all the address decoding, backpressure, clock domain and interface differences, and arbitration if multiple hosts connected to a particular agent try to access that agent simultaneously. Both host and agent interfaces must be associated with a clock interface, since all memory-mapped transactions must be synchronous. While not required, it is recommended that all host and agent interfaces are also associated with a reset interface. Warnings will be displayed in Platform Designer if there is no reset interface association, but the system design can still be generated and function. These are the basic signals available for use in an Avalon host interface. The only required signals are the address and wait request signals. Wait request is required because the host must have the ability to be stalled by the interconnect if the agent being accessed requires more cycles to respond to a command, or because of arbitration with another host accessing the same agent. The rest of the signals are optional. When you create a custom host component, you only need to use the signals required for the functionality of your component. For example, if your component only needs to read data from a memory, there is no need to include the write and write data signals in the component's design. The byte enable signals can be used for masking off which bytes to read or write, and the lock signal gives the host exclusive access to an agent, preventing other hosts from accessing it. Finally, the response signal can be used to verify whether a data transfer was successful or not. The agent signaling is very similar to the host signaling. Unlike the host interface, none of the signals are explicitly required, giving you maximum flexibility when designing a custom agent component. While wait request is required to stall a host, it is optional for an agent. This is because the interconnect can stall a host automatically if needed, based on interface properties of the agent that we'll discuss shortly. By including the wait request signal on an agent interface, the agent component has a manual control for stalling a host. The address signal is optional on an agent as well. We'll see why this is in a moment. So at a minimum, a host interface must have an address output and a wait request input signal. If the host is to support read transfers, then it needs the read enable and read data signals. If the host is going to support write transfers, then it needs the write enable and write data signals. For an agent, as mentioned, wait request is only needed if the agent is to have manual control over stalling a host. The address input is only required if there are multiple addressable locations within the agent component. For example, if an agent component has multiple register locations for control and status checking, the address input would be required. However, if the agent has only a single readable or writable location, address is not required. The base address location set in Platform Designer is sufficient for any host to find and access the agent. To support write transfers, the write enable and write data signals are needed. For read transfers, only read data is required. With only read data, read transfers don't need to be qualified with an enable, so the agent will always return data pointed to by the specified address. There are two fundamental types of transfers through Avalon memory-mapped interfaces, reads and writes. Remember that transfers do not occur directly between hosts and agents. Thus, when we refer to host and agent read and write transfers, we mean that the transfer happens between the interface and the Platform Designer interconnect. Beyond that, there are variants of the fundamental transfers. These include having a fixed or predetermined number of wait states, or having a variable number of wait states. Wait states mean that the agent takes one or more additional clock cycles to return data on a read or complete the writing of data on a write. With variable wait states, the agent issues the wait request control signal to the interconnect, indicating that wait states are needed before continuing the transfer. The fundamental transfers can also be adjusted and optimized in a similar manner to Avalon Streaming credit interfaces using the waitrequestAllowance property. There are also some advanced transfer types available. Pipeline transfers allow for multiple read transfers to occur in sequence, with the agent validating the read data as it is sent to the interconnect. Burst transfers lock a host to an agent for a fixed number of transfers before releasing the agent. These advanced transfers require additional control signals to be used in the interface. Let's start with a fundamental read transfer on the host side of the interconnect. After a rising clock edge, the host asserts the read enable signal and specifies an address to read as seen at point B in the timing waveform. After asserting the control signals, the host must honor wait request by stalling the transfer, holding the read enable and address signals constant until wait request is deasserted. This is seen at cycle D and point E. Once wait request is deasserted after clock cycle F, the host samples read data on the next rising clock edge, and the transfer ends. This is seen at clock cycle G. An interface may include the response signal. This 2-bit signal can provide information back to the host on the success or failure of a data transfer. The encoding of this signal is shown here. If one side or the other does not include the response signal, the interconnect will include logic to handle its use with the appropriate interface. For a read transfer, as shown here, the response is sent back to the host along with read data. For a write transfer, an additional signal, named write response valid, is required to qualify the write response one cycle after the write occurs. See the Avalon specification for examples of write responses. Here is an example of a fundamental host write transfer. This time, after rising clock edge A, the host asserts the write enable signal, the address to write to, and the data to write, as seen at point B. During the transfer, the host must again honor wait request. If asserted, the host must stall its transfer by holding all the control signals, including write data, constant until wait request is deasserted. Once deasserted after clock cycle F, the write occurs on the next rising clock edge. Now, here is a fundamental read transfer from the agent's point of view. After rising clock edge A, the Platform Designer interconnect asserts the read enable signal and the address to be read. Note that this address will be translated by the interconnect to be specific for the agent's local register map, so it may be different from the address issued by the host. We'll look at how addressing works between hosts and agents later. By the next rising clock edge, the agent must present the data from the address specified, at which point the transfer completes. In this case, the transfer occurs in a single cycle. A fundamental write transfer from the agent's point of view operates in a similar manner. After a rising clock edge, the interconnect asserts write enable, the address to write to, and the data to write. By clock edge D, the agent must accept the data, ending the transfer. In this case, the transfer again occurs in a single cycle. Like the other standard interfaces discussed so far, Avalon memory mapped interfaces feature several properties that can be used to adjust an interface's implementation and functionality. In this training, we'll discuss the ones listed here. Again, check the Avalon specification for other available properties. The read wait time and write wait time properties are used to add fixed latency to a data transfer. When a read or write command is issued to an agent, the value of these properties indicate exactly how many clock cycles or nanoseconds elapse before the agent provides the data on reads or completes the storage of data on writes. The timing units property is used to indicate if the value of read wait time or write wait time is in cycles or nanoseconds. Clock cycles is the most common unit used for these properties. Here is an example of a fixed latency read data transfer from the agent's point of view. If an agent cannot execute a transfer in a single cycle, the interface can be adjusted with read wait time to support a fixed latency corresponding to a defined number of wait states before read data is available. If read wait time is greater than 0, the read enable and address signals remain asserted through all the wait states. In this example, read wait time is set to 2 clock cycles. This means that the command arriving on clock cycle C will produce valid data 2 cycles later. Cycles C and D are considered the wait states, and D and F are the additional cycles beyond when the command is received by the agent. Once the additional cycles elapse, the data available on the read data output is sampled on clock cycle F. If the number of wait states required is unknown or could vary, then the agent must implement a wait request output. A data transfer where the agent controls the wait request signal is referred to as a variable latency transfer. As long as the agent asserts the wait request output, the transfer stalls. Once wait request is deasserted, the agent must present the data on the next rising clock edge. In this usage, you can think of wait request as similar to an active low data valid signal for the read data. Like read transfers, write transfers also support fixed and variable latency. With a write wait time of 1 in the top example, the write issued on cycle D does not occur until cycle F, making D the wait state and F the additional cycle. In the bottom example, the agent asserts wait request until after cycle C, causing the stalled write to occur on cycle D. Here's an example of how arbitration works with the Platform Designer interconnect. In the live class, we'll discuss how arbitration logic is automatically added to the Platform Designer interconnect when more than one host interface needs to access a single agent interface. We'll also look at the options for setting up the arbitration algorithm to decide which host gets ownership of an agent in this situation. In the example shown here, 2 hosts, H1 and H2, are trying to access a single agent. Notice that both hosts assert their control signals, address and read enable, for the same clock cycle. For the purposes of the example, let's say that H1 wins the arbitration. That means that the H1 read data is available immediately to that host and the read transfer completes. From H2's point of view on that same clock cycle, the interconnect asserts the wait request signal, stalling H2 and forcing it to continue asserting its control signals. Before the next cycle, wait request is deasserted and H2 receives its data, completing the transfer. The bottom of the diagram illustrates this from the agent's point of view. First, it sees the valid address issued by H1 and supplies the appropriate data. It then sees the address issued by H2 on the next clock cycle and provides the requested data. In this case, the arbitration logic in the interconnect automatically handles the control of wait request to both hosts, but there's no reason why fixed or variable latency couldn't be implemented as well. The latency would be added along with the arbitration logic control to make sure the arbitration algorithm is implemented correctly and both hosts get their data as soon as the agent is able to supply it. The behavior of the wait request signal can be adjusted with the waitrequestAllowance interface property. As just illustrated, normally, when wait request is asserted to a host, the host must continue asserting its control signals until the next clock cycle after wait request is released. However, if the waitrequestAllowance property is greater than 0, commands can be issued and completed even while wait request is asserted, up to the value of the property. The use of and need for this property is somewhat similar to the use of the Avalon Streaming Credit Standard interface discussed earlier. By not requiring data transfers to stall immediately when wait request is asserted, additional pipeline stages can be added to an interface, allowing for easier time enclosure, improved performance, and more opportunities for retiming in hyperflex-based devices. In the example shown here, waitrequestAllowance is set to 2. Even though waitRequest is asserted, the host issues 2 write commands at clock cycles C and E, corresponding to the waitrequestAllowance value, both of which will complete successfully. However, the host cannot issue any further commands if waitRequest is asserted for more than 2 clock cycles, as is the case with the 3rd cycle at cycle F. The host must deassert its control signals for this cycle. See the Avalon specification for more examples of this property's use. So from this discussion, you can see that the functionality of a memory-mapped interface really relies on the signals implemented. When you're creating your own custom components, you only need to include the signals needed to achieve the desired functionality. You don't need to add dummy signals to follow the standard. The generated Platform Designer interconnect will handle signal mismatches for you automatically. The examples here illustrate this. The upper left host interface provides full read and write capabilities for the host component. The lower left interface provides only read access for the host. Again, notice that waitRequest is required for both host interfaces. The upper right agent interface provides read-only capabilities, so that component may be a ROM or a system input interface. It includes variable latency control because it implements the waitRequest signal. Finally, the lower right agent interface is a write-only interface. It may include fixed or no latency since waitRequest is not used. There's no way to tell for sure without checking the interface's properties. It also does not include an address input, so that means a host can only write to a single fixed address location specified in the Platform Designer system design. We'll now take a look at how addressing works through the Platform Designer interconnect with memory-mapped interfaces. Addressing is always based on the read or write data bus width of the host and agent. By default, a memory-mapped host uses byte addressing. This means that a 32-bit host must increment addresses by 4 to read or write the next 32-bit location. Agents, however, use word addressing by default, where the word size matches the data bus width. Thus, the interconnect always increments each address on the agent side by 1 to get to the next addressable location. In the example shown here, both the host and agent data buses are 32 bits. If the host were to issue a read or write request to address location 8, this address would correspond to word address 2 on the agent as shown. The conversion of byte to word addressing is handled automatically by the Platform Designer interconnect. Note that if the host needs to write only individual bytes and not the entire agent word, both sides of the interconnect would need the byte enable signal. As mentioned, agent accesses are word-wide, so byte enable would be required to prevent overwriting other bytes in each agent word location. While byte addressing for the host and word addressing for the agent are the defaults, Platform Designer allows you to change this behavior when creating your own custom components. Thus, if both host and agent use either byte or word addressing, you can have a one-to-one mapping between them. The Platform Designer interconnect performs dynamic address alignment by default. If the host and agent components are of different widths, the interconnect will access the agent as many times as needed to fill up the master's data bus, buffering data and taking additional clock cycles as needed. For example, with a 32-bit host and an 8-bit agent, when the host issues a read or write to the base address of the agent, 4 bytes are needed to fill the host's data bus. So, 4 bytes on the agent are accessed at locations 0 through 3. The host issues a single command to the interconnect, but the interconnect will need to issue 4 commands to the agent. The interconnect will stall the host until all 4 accesses to the agent are complete. If the host then needs to access the next 32 bits of data, it increments the address by 4 as usual. The data at agent address location 4 is accessed in a single cycle because there are no higher address locations in the agent. So the higher order bytes returned to the host are undefined or don't care. Here's another example that shows how dynamic bus sizing is used with host and agent addressing, again showing a wider host with a narrower agent. If a 32-bit host accesses a 16-bit agent, a single host access corresponds to 2 accesses to the agent, with host byte address 8 corresponding to agent word addresses 4 and 5. Again, the interconnect will stall the host until both accesses to the agent are complete. Now, what happens with a narrower host and a wider agent? As before, the 32-bit host continues to issue addresses aligned to multiples of 4 bytes. However, the address issued to the wider agent, in this case a 64-bit component, will only increment when the host address increments by 8 bytes. In the example shown here, the host is issuing address location 8, which corresponds to word address 1 on the agent. Word 2 on the agent would not be accessed unless the host increased the requested address to hex 10. If this is a read, the full 64-bit word is read from the agent, but only the lower 32 bits are presented to the host. The byte enable signal is not required because the interconnect will present the correct bytes to the host. However, if this is a write, while the host still does not require byte enable, the agent would, since a write would overwrite the full 64 bits instead of just the lower 4 bytes. The interconnect would automatically handle byte enable to the agent to ensure only the lower 4 bytes get written. As mentioned, even with a wider agent, the host still increments addresses by 4 to match its 32-bit data bus. So if the host specifies an address of C, the full 64 bits of word 1 are again accessed on the agent. Only a single read or write access is still performed on the agent, and only the appropriate bytes, in this case bytes 4 through 7, are presented to the host on a read. Once again, for writes to the agent, the byte enable signal would be required. As mentioned, when creating a custom component, you can adjust how the addressing works from the default of byte addressing for the host and word addressing for the agent. Shown here is part of a tool called the Component Editor, found in Platform Designer. You use this tool to specify the HDL code to create custom components and specify how the component's interfaces will work, including the addressing scheme. For example, an agent uses word addressing. To change this to byte addressing, you'd change the address units property from words to symbols. Like Avalon Streaming, you can change the symbol size to any value you want. For byte addressing, change the bits per symbol property to 8. A standard host accessing this agent would still increment addresses based on the byte width of the host's data bus, but the address would be translated to the specified symbol width on the agent side. You can also change symbols to words on a host interface. In this case, the host would only need to increment its address by 1 to access subsequent locations on an agent. If a host tries to access an undefined address location, the read or write command is routed to what's referred to as a default agent. This can happen if there are gaps in the host's address map, if the host accesses an address outside its address map, or if the host tries to perform a write on a read-only agent, or vice versa. The default agent is an agent in the host's address map designated to respond in these situations. The default agent is the lowest address agent in the host's memory map if it is not explicitly specified. The screenshot shows how you can choose a different default agent in Platform Designer. The default agent is chosen to provide the response signal back to the host, indicating an error due to the reasons given. If the default agent does not use the response signal, the interconnect will send the response signal back to the host. If the host does not use the response signal, there is no way for the host to know it issued an incorrect address. The Avalon Memory Mapped standard supports some more advanced transfer types. Let's take a look at pipelined transfers. A pipelined transfer is a method of having multiple data transfers occur simultaneously to improve system performance. A new command is issued by the host before the results of a prior command are returned. Avalon only supports in-order pipelined transfers. The data for each read or response for a write must return in the same order the commands were issued. As we've seen, a transfer is made up of an address phase where the address is presented by the host, or the Platform Designer interconnect, and a data phase where the Platform Designer interconnect or agent returns the data on a read or accepts the data on a write. In a non-pipelined transfer, the address and data phases occur simultaneously and end together. In a pipeline transfer, the address and data phases are separated. The pipeline logic added for this type of transfer stores the multiple requests and issues them in order when the addressed agent can respond. The address phase can be extended using properties discussed earlier, or through manual control of the wait request signal by the agent. The data phase occurs a fixed or variable number of cycles after the address phase is complete. The number of cycles between the address and data phases is referred to as the pipeline latency. These diagrams illustrate how pipeline latency is controlled. As mentioned, the address phase can be controlled with an interface property or control of wait request. Additional cycles here are referred to as wait states, as discussed earlier. But for a fixed pipeline latency between the address and data phases, an additional property called readyLatency is used. When this is set, data is always available readyLatency number of cycles after the address phase, essentially setting the length of the pipeline. For reads, the agent must be designed to always provide valid data at this point because there are no other signals used to validate the data during the data phase. For writes, a response is returned to the host with a validation signal. If the agent cannot always provide data at the same fixed cycle or wants to control the number of pending transfers, variable latency can be implemented. For variable pipeline latency, the agent must control the wait request signal whether wait states are needed during the address phase or not. Then, when data is available, the agent deasserts wait request and provides the data with an additional signal named read data valid. The host only accepts data validated with this signal. For writes, the agent again provides a validated write response. For detailed timing waveforms of both fixed and variable latency pipelined transfers, see the Avalon specification. The other supported advanced transfer type is a bursting transfer. A bursting transfer is used by a host to gain uninterrupted access to a particular agent. This allows a larger block of data to be sent without having to use separate transfer requests and without the danger of another host making a request to the same agent and interrupting or even corrupting the data from the first. The Avalon standard supports both read and write bursts. To perform a burst transfer, the host specifies only the starting address to access for the burst and the number of transfers to perform using an additional signal named burst count. When a bursting transfer is granted, the arbitration logic in the system interconnect locks the host to the addressed agent until the number of transfers specified for the burst is complete. The interconnect automatically increments the address issued to the agent a number of times based on the value of the burst count signal. The entire burst must be within the address space of the single locked-on agent, and there is no method for out-of-order transfers. If wait states are needed, the agent must control wait request manually, and if read bursts are to be performed, the read data valid signal is also required. Read bursts operate very similarly to pipelined transfers with variable latency, so the data returned during a read burst must be validated. A burst transfer, even though it is made up of multiple transfers, still counts as only a single share for the arbitration algorithm. In the instructor-led class, you'll learn more about how this share-based arbitration mechanism works. Here is a summary of the additional signals required for these advanced transfer types. The burst count signal, asserted at the beginning of a burst, indicates how many burst transfers will take place. As mentioned, read data valid indicates that the incoming read data from a previous read transfer request is valid. The write response valid signal was not discussed in detail, but it is used to validate the response signal if pipelined writes are performed. Remember that the exact signal role names listed here are used when building custom components in Platform Designer. You'll learn more about this in the live class. With that, we've now discussed the two main types of Avalon standard interfaces, streaming and memory mapped. In the example system shown here, you can see a host, designated as a processor, controlling and accessing a number of agents, some to just read and write their contents, like the RAM, and some to configure and check their status, like the FIFO. Once the components with the agent interfaces are configured, streaming data transfers can occur between them. As you'll learn in the live class, these standards are complementary to each other and can be used together to build up more complex system designs like this. There are a few other interface types that make up the Avalon standard. Avalon conduit interfaces are signal groupings that don't conform to any of the other standards. They are typically exported out of a system to connect to other parts of a design or device I/O pins. A tri-state conduit interface allows for control and access to external devices on a tri-state bus. Through the use of built-in IP, signals on the tri-state bus can be shared across multiple devices on the bus, saving FPGA device pins. Finally, an interrupt interface allows an interrupt sender to send an interrupt signal to an interrupt receiver, such as a processor, for servicing. These interface types are discussed in more detail in the live class. For more information about all of the Avalon interface types discussed, see the Avalon Interface Specifications document available on the Intel FPGA website. Besides general information about signaling in an Avalon interface, you'll find usage examples and detailed waveforms to help you in creating a compatible interface for your own custom components. To finish up this training, let's take a short look at the Arm AMBA AXI standard. The Advanced Extensible Interface, or AXI, is an interface standard licensed from Arm for use with Arm processors and related IP. Intel FPGA SoC devices feature a hard processor system, or HPS, that consists of a dual-core Arm Cortex-A9 processor or a quad-core Arm Cortex-A53 processor. The HPS uses the AMBA 3 AXI interconnect interface standard to communicate with components in the HPS as well as with components in the FPGA fabric. The HPS is added to a Platform Designer system just like any other component, so Platform Designer fully supports the AMBA AXI interface standard. There are actually a number of supported versions of the standard: the AMBA 3 AXI standard, the AMBA 4 AXI standard, a light version of the AMBA 4 AXI standard, and a streaming variant. The AMBA 4 AXI standard has all the same base features as the AMBA 3 AXI standard, but has a few changes to it and some added features. These include quality of service information for transactions, multiple region support to allow a single physical agent interface to support multiple logical interfaces, each using different locations in the address map, and user-defined sideband signaling. The light variant of the AMBA 4 AXI standard simplifies interface designs that use the standard by limiting the data width, removing the options for burst transactions, and by using fewer signals. The additional AMBA 4 AXI standard features and the light variant of the standard will not be discussed in this training. As you'll learn in the live Platform Designer training, the interconnect generated by Platform Designer allows any component to communicate with any other component as long as they both use one of the standard interfaces. The table shown here lists the automatic conversions performed by the generated system interconnect to allow for this communication. Thus, memory-mapped ARM standard interfaces and Avalon-based components can all communicate with each other. Streaming interfaces, however, are not converted. The Arm AMBA AXI standards have a number of differences and additional features over Avalon, so if components using either of the standards are communicating with each other, there will be restrictions on what features will work and how they will work. See the Platform Designer user guide, linked at the end of this training, to learn how transactions between Avalon and the Arm AMBA AXI interfaces will operate. The key features of the AMBA AXI standard are listed here. The Arm AMBA AXI standard is most suitable for high bandwidth, low latency designs without the need for complex bridges between components. It features separate address and data phases for every transaction, unlike Avalon, where additional signals are required for pipelined transfers. Separating the address and data phases for all transactions allows for a number of features, including the ability to perform out-of-order data transfers. The standard supports bursting for all data transfers with only the starting address location issued to the agent. The AMBA AXI standard also supports data transfers that are not aligned at word boundaries through the use of byte strobes. Finally, the standard supports the idea of secure transactions where only approved hosts and agents can communicate with each other. Components that are not deemed secure cannot communicate with secure components. This is ARM's Trust Zone technology. Platform Designer supports Trust Zone and includes options for how non-secure components, such as any component using an Avalon interface, will be able to interact with secure components. When discussing Arm AMBA AXI interfaces, some additional terminology is required. Operation of the standard consists of the use of separate channels. A channel can be thought of as a phase of operation for the interface. Each channel includes a collection of signals that performs a particular function on the interface during that phase of operation. The 5 channels are read address, write address, read data, and write response. As shown here, all corresponding channels must be used to perform a read or write. The names of all the signals in each channel are prefixed with the letters indicated to make it easier to identify them. A transfer is a single exchange of information over one of the 5 channels. For example, the sending of read data from an agent back to a host. A complete transaction consists of a burst of either 2 transfers for reads or 3 transfers for writes. For a read, one of the transfers is for the address channel and the other is for the data channel. Multiple data transfers can be performed, but there must be at least one. For a write, the first 2 transfers are for the address and data channels like on a read, while the third transfer is for the separate response channel on a write. You'll see how these separate channels and transfers work in a moment. An active transfer is a read or write transfer that has been initiated, but the handshaking for the transfer, discussed in a moment, is not yet complete. Finally, An active transaction refers to a transaction where the address transfer has completed, but the other transfers have not. For a read, this means that the last data transfer has not yet completed. For a write, this means that the last response transfer has not yet completed. All Arm AMBA AXI interface channels support a simple handshaking mechanism. This allows both hosts and agents to have complete control over the flow of information between them. The source, which is whichever interface initiates a transfer on any of the channels, asserts the valid signal. The destination indicates that it accepts the transfer of information by asserting ready back to the source. The transfer on any of the channels occurs on the next rising clock edge after both valid and ready are asserted. These waveforms illustrate how the handshaking mechanism works. The ready and valid signals are available on each of the 5 channels and can be asserted in either order or at the same time to initiate a data transfer. The source asserts valid with the data it's sending, and the destination asserts ready when it is ready to receive the data. The order of these events does not matter. With the handshaking mechanism in mind, here is how a full write transaction works. As mentioned, there are 3 separate channels for a write. During the write address phase of the transaction, the host issues the write address signal called AW_adder, and other control signals not shown here, along with AW_valid. For this example, the ready signal from the agent, AW_ready, is already asserted. Next is the write data channel. The diagram shows this occurring 2 cycles after the write address transfer, but it could just as easily occur on the next clock cycle. For the write data transfer, the host asserts the write data, WData, along with the write valid signal, WValid. In the example, the agent has already asserted the write ready signal, WReady, back during the write address channel, so the data transfer occurs immediately. Only 2 words of data are transferred here, but any number of burst transactions can occur during the write data transfer. Finally, the agent responds back to the host on the write response channel using the bResponse and bValid signals. bReady is already asserted by the host, so the response is immediately accepted. Here is how a read transaction works. The read address channel has similar signaling to the write address channel. AR_adder and AR_valid are issued from the host, and the host looks for AR_ready from the agent. In the read data channel, the agent issues the read data, RData, along with RValid and the RResponse signal to indicate whether the read access was successful. Again, while only 2 reads are shown here, there could be a whole sequence of burst reads. To finish up this look at the Arm AMBA AXI standard, it's important to understand which protocol to use in your custom components. How do you choose? If you are looking for something simple and easy to implement, Avalon is the way to go. The Arm AMBA AXI standard has many more features and capabilities than Avalon, but it can be much more complicated to implement. If you have existing Avalon-based systems or components, use Avalon. If you have legacy IP or want to communicate directly with an ARM-based device, such as the ARM Cortex-A9 or A53 found in Intel FPGA SoC devices, use the Arm AMBA AXI standard. If you want locked or exclusive access to an agent, use the Arm AMBA AXI standard. ARM's interface standard has additional features beyond the simple locking mechanism found in Avalon. Ultimately, though, you are free to mix and match interface standards however you want, but our best recommendation is to use Avalon wherever possible. This is just a taste of the features and functionality available in the Arm AMBA AXI standard. To learn more, see the Arm AMBA AXI protocol specification found on the ARM website. Accessing the PDF requires a free registration. As mentioned at the beginning, this training is a required prerequisite for the Introduction to Platform Designer instructor-led training. If you are not registered for this training and are interested in attending a future session, you can find details about this live training class and register for it at the first link shown here. To learn more about standard interfaces, creating custom components, and the Platform Designer tool itself, see the Platform Designer User Guide, as well as the many Platform Designer-related online trainings available in our course catalog. You can use the links shown here for direct access. Intel FPGA provides many additional technical support resources besides technical training. The technology landing pages give you quick access to all the resources you'll need for a particular topic or application. Check out the online Intel FPGA forums. They're a great place to connect with other users to share experiences and find solutions to common issues. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Licensing Support Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. The Intel FPGA technical training team is constantly looking for ways to improve our training materials. We want to create the material and content that work best for you. Your feedback is a very important part of this process. If you'd like, please provide feedback to fpgatraining@intel.com. Thank you in advance for your feedback. My name is Steve, and I want to thank you for taking this online training about the standard interfaces used in Platform Designer.